Hi everyone, we'll be taking a look at the generalized Black-Scholes model now. I'm going to start off by reminding you of a derivation of the Black-Scholes PDE and its solution that you've probably seen. There are some issues with that derivation, however, so after that we'll do a proper derivation. Simultaneously, we'll extend the Black-Scholes PDE to the multi-asset case, where the underlying assets are driven by a standard multi-dimensional Brownian motion. We'll also have a look at delta hedging. And then finally, we consider what the Black-Scholes PDE looks like if we model each asset with its own one-dimensional Brownian motion, where these Brownian motions are correlated. So let's start by a derivation of the Black-Scholes PDE. The derivation here is a naive derivation. It is not completely correct mathematically, but there is a lot of intuition in it, and it can be found in many textbooks. The basic assumptions are as follows. There is only a single share, S, and that share follows geometric Brownian motion dynamics. In other words, ds over S is equal to mu dt plus sigma dwt, where mu and sigma are constant. We also assume that the share pays a continuous dividend yield of Q, where Q is constant as well, and that means that in a small interval from t to t plus dt, the share pays an amount of Q times st dt in dividends. In addition, there is a bank account, and the riskless rate of interest for that bank account, continuously compounded, is R. Consider now a European-style derivative d on that share, whose payoff dt depends only on the stock price at the expiry t. In other words, it's a function phi of the terminal stock price. For a vanilla call, for example, the payoff phi st is just the maximum of st minus a strike and 0. But the derivation here holds for very general payoffs, not just for vanilla calls and puts. Construct now a portfolio pi consisting at time t of one derivative d and minus delta t shares S. In that case, the value of the portfolio at time t is pi t is equal to the value of the derivative minus the number of shares, delta t, times the share price, st. A small time dt later, the value of the portfolio will change, and the amount by which it will change, i.e. d pi t, will be the change in the value of the derivative minus delta times the change in the value of the share. Moreover, because we are short delta many shares, we also have to pay the dividend yield for delta many shares. In other words, we have to pay delta times Q times S dt. And hence the change in the portfolio value is given by this expression here. We also assume that the time t value of the derivative, dt, is a function of the time t and the stock price at that time, st. We further assume that we're able to apply Ito's formula to this function d. In other words, that d is once continuously differentiable in the t variable and twice continuously differentiable in the s variable. In that case, by Ito's formula, d dt is partial dd by dt dt plus partial dd by ds times ds plus a half partial d squared d by ds squared times d quadratic variation of s. Of course, d of the quadratic variation of s is just sigma squared s squared dt. It follows therefore that d pi t, which we saw on the previous slide, is equal to d dt minus delta times dst plus qst dt, is equal to the following expression: partial dd by dt plus half sigma squared s squared d squared d by ds squared minus delta t qst dt plus partial dd by ds minus delta times ds. Suppose now that we rebalance our portfolio continuously, in other words, that we dynamically hedge our portfolio to ensure that the number of shares that we are short at time t, delta t, is always equal to partial dd by ds at that time. Note that partial dd by ds depends also on t and on st. In that case, this term here disappears. Now the Brownian motion sits only in dst, it does not sit in dt. So if this term disappears, then there is no noise at all. In other words, we just have a dt term. In that case, the instantaneous return of the portfolio is locally riskless because of the absence of a Brownian motion. Now comes the crux. By no arbitrage considerations, if the portfolio is locally riskless over an infinitesimal period from t to t plus dt, then it must earn the riskless rate over that period. In that case, it must be the case that d pi t is equal to r times pi t times dt. So when the portfolio is locally riskless, i.e. when delta is equal to partial dt by ds, we have two expressions for d pi. On the one hand, d pi is equal to this term here, because this term here disappears. And on the other hand, it's equal to r times pi times dt. Thus we have the following equation. Now this equation holds only when the number of shares that we are short, namely delta, is equal to partial d by ds. In other words, when we have removed the noise. Note that we can cancel the dt's. Moreover, the value of the portfolio pi is just equal to the value of the derivative minus the number of shares times the value of the share. And since delta is partial d by ds, we can rearrange the right side and the left side to obtain the following partial differential equation, as you can easily verify. This is the Black-Scholes PDE, and it has a boundary condition, which is a terminal condition, namely the value of the derivative at the maturity or expiry capital T, when the stock price is S, is just equal to the payoff phi of S. Now note that we haven't talked about the bank account here at all. However, delta, the number of shares that we are short, is changing over time because the partial derivative depends on time as well as on the stock price. Since the number of shares that we hold is changing continuously, we must be buying and selling shares, and that must be financed by the bank account. We'll give a proper derivation of the Black-Scholes PDE and generalize it to the multi-asset setting a little later. Let's now have a look at an important result about the log-normal distribution. This result is important mainly because, particularly in the early days of mathematical finance in the 70s and 80s, everything was considered to be log-normal. For example, futures prices, swap rates, cap rates, etc. were all modeled log-normally, to such an extent that it became important later to construct arbitrage-free models that would lead to those market variables being log-normal inside the model, in agreement with market practice. We'll have a look at such market models for interest rates later in this course. Here is the result. Suppose that x is log-normally distributed, i.e. that the log of x is normally distributed with mean mu and variance s squared. Let k be a positive constant. Then the probability that x is greater or equal to k is equal to nd minus, and the expected value of x minus k plus is equal to the expected value of x times nd plus minus k times nd minus. Here d plus and minus are given as follows. D plus has a plus sign, d minus has a minus sign. And the expected value of x is given by a moment generating function argument over here as e to the mu plus a half s squared. For a call option with strike k, these look like the probability of the option expiring in the money and the price of a call option. I think the proof is pretty straightforward, if somewhat messy, and I will let you go through it yourself. One thing that may be worth mentioning, however, is the following. We prefer to use the expression expectation of x rather than its actual value e to the mu plus half s squared in the above formula, because very often x will be the terminal value of some martingale, in which case the expected value of x is simply its initial value, so that it needs not be computed. Using this log normal formula, It is now easy to derive the Black-Scholes formula for vanilla options. Suppose now that C is a European call option with strike K and maturity capital T on a non-dividend paying stock S. Under the risk neutral measure Q, the dynamics of discounted S, i.e. S bar, are given as follows. It follows that S bar is a martingale, as it ought to be under the risk neutral measure. Applying Ito's formula to the logarithm of the discounted stock price, we obtain the following. And this stochastic differential equation is very easily solved simply by integrating both sides to obtain the following. The logarithm of the discounted terminal stock price is normally distributed with mean ln S0 minus half sigma squared capital T and variance sigma squared capital T. Because S bar is a martingale, its expectation under the risk neutral measure is S0. The payoff of the derivative, in other words its value at the terminal time, is simply St minus K plus. According to the risk neutral valuation formula, the initial value of the call, C0, is simply the expectation of the discounted payoff. Here we've discounted both the terminal stock price as well as the strike price. Using the log normal formula, we obtain the following. Now K bar, discounted K, is simply e to the minus RT times K. And the expectation under the risk neutral measure of S bar is S0, and hence we obtain the following result. Here d plus and minus are given as follows, and simplifying the expression inside the logarithm, we obtain the following well-known result. That gives the price for a vanilla call option. For a put option, we can simply use put-call parity, which I've stated here as follows. If you own a call option, you may have to exercise it, in which case you have to pay the strike. In order to pay the strike K at time capital T, you need to own K e to the minus RT right now. So on the left side here, we have a call option plus the cash needed to be able to exercise it at maturity. On the right hand side, if we have a put option, we may want to exercise it in the future, in which case we have to sell a share for the strike. In that case, we need to own this share. So on the right hand side, we have a put option plus what we need to exercise it. So put-call parity says that a call option plus the cash that you need to be able to exercise that call option is equal to a put option plus the share that you need in order to be able to exercise that option. Using the symmetry of the standard normal distribution, it then follows very easily that the price of a put option is given as follows.